In this video, we are going to take a look at the concepts of real numbers. These are the topics that we are going to go through. Some of them may have been removed from syllabus, but still let's try and go through all of them to get a bit more in-depth understanding of how real numbers work and operate. So real numbers are made up of rational and irrational numbers. So firstly, we'll take a look at what are rational and irrational numbers along with few examples, followed by Euclid's division lemma. We'll briefly touch upon this concept. Then we'll take a look at the fundamental theorem of arithmetic, followed by HCF and LCM. Euclid's division lemma is mainly used to calculate HCF of numbers. Here our attempt would be to see if there are any simple ways to calculate HCF and LCM. Then we'll take a look at proof of irrationality of certain numbers. And lastly, rational numbers and their decimal expansions. So, Euclid division lemma and rational numbers and their decimal expansions may have been removed from the syllabus, but as mentioned, let's try and go through all these concepts, and they are useful in one way or other in the coming chapters and further studies in mathematics. So, let's go through all of them. Real numbers are the main topic of study in this chapter, and real numbers are made up of two types of numbers, rational numbers and irrational numbers. So rational numbers and irrational numbers put together make up real numbers. So what are rational numbers? These are the numbers that can be expressed in P by Q form, where P and Q are integers and Q is not equal to 0. If Q is equal to 0, then the value of this fraction would be undefined. So Q cannot be 0. So rational numbers are the ones that can be expressed in P by Q form, where P and Q are integers. Rational numbers can also be defined as numbers whose decimal expansion is terminating or non-terminating repeating or recurring one. So these are the technical words. So let's try to understand in simple words. What do we mean by decimal expansion terminating? When we start dividing P with Q, at some point of time during the division, the remainder becomes 0 and the division ends. That is the meaning of decimal expansion getting terminated. And for non-terminating recurring type of decimal expansions, the remainder will never become 0 during the division, and the division keeps going on, and it never ends, never terminates. But a digit or a group of digits keeps on recurring or repeating. Now coming to irrational numbers. These are the numbers that cannot be expressed in P by Q form, where Q is not equal to 0, obviously. So P and Q here are integers, and we can't find two integers to represent the irrational numbers in P by Q form. And irrational numbers can also be defined as numbers whose decimal expansion is non-terminating and non-recurring decimal expansion. So for irrational numbers, the division keeps going on. The remainder will never become 0, and the division keeps going on, and the digits also will not recur or repeat when it comes to irrational numbers. Now let's see a few examples of rational numbers and irrational numbers. 1 by 2, 3 by 4, minus 5 by 8, and minus 7 by 10 are the examples of rational numbers whose decimal expansion terminates. That means that when we start dividing 1 with 2 or 3 with 4 and minus 5 with 8 and minus 7 with 10, the division ends. At some point of time, the remainder becomes 0 and the division ends. So their decimal expansion terminates. For 10 by 3, 1 by 7, the division never ends. The remainder will never become 0 when we start dividing 10 with 3 or 1 with 7. So the division keeps going on, and a digit or certain group of digits keeps on recurring or repeating. And here are the examples of irrational numbers. Pi is the well-known and popular irrational number. And here are a few other examples. So usually pi is taken as 22 by 7. But 22 by 7 is only an approximate value of pi. It is not the actual value of pi, because pi is an irrational number and it cannot be expressed in p by q form. So we can't find two integers p and q to represent pi in p by q form. Similarly, the approximate value of root 2 that we take is 1.414. That is only an approximate value. For root 2 also, we can't find two integers p and q to represent root 2 in p by q form. And similarly for other examples. Now, let us see the actual division of 1 with 2 and 3 with 4 and few other examples. Let's do the actual division of some of these numbers and then try to understand the meaning of decimal expansion getting terminated or decimal expansion being a non-terminating repeating one. So let us start with our first example, 1 by 2, 2 dividing 1. So 2 doesn't go in 1, so we have to put a 0 and decimal point and make this as 10. And 2 5s are 10. And the remainder becomes 0 here. So the decimal expansion terminated. In simple words, the division ended as the remainder has become 0. So we have 0.5 as the quotient, 0 as the remainder. So here the division has ended as the remainder has become 0. And this is the meaning of decimal expansion being terminated. And simple words, the division ends as the remainder has become 0. Now let's take another example, 3 by 4, 4 dividing 3. So 4 doesn't go in 3, so we put a decimal point and make this as 30. And 4 sevens are 28. So the remainder is 2 here, and we have to make this as 20. And 4 fives are 20. And the remainder becomes 0. So these two are examples of rational numbers whose decimal expansion terminates. In simple words, at some point of time during the division, the remainder becomes 0 and the division ends. Now let's see a couple of examples of rational numbers whose decimal expansion is non-terminating but a recurring one. Now let's take the example of 10 by 3, 3 dividing 10. So 3 times 3 is 9. We get 1. And 3 doesn't go in 1, so we put a decimal point and make this as 10. And again, 3 times 3 is 9. We get back 1 and adding 0. 3 times 3 is again 9. and 1 0. So as you can see, the decimal expansion, or in simple words, the division never ends here. We can keep going on and on. We keep getting the same results, and the digit 3 keeps on repeating here. So this is an example of a rational number whose decimal expansion never terminates. In other words, division never ends, and the digit 3 keeps on repeating. Now let's take another example, 1 by 7. So 7 dividing 1. 7 doesn't go in 1, so we put a 0 dot decimal and make this as 10. And 7 goes in 10 one times. So 7 ones are 7. So we get 3 as the remainder, making this as 30. 7 fours are 28. We get 2 as the remainder, making this as 20. 7 twos are 14. We get 6 as the remainder, making this as 60. 7 eights are 56. So we get 4 as the remainder, making this as 40. And continuing here, 40. 7 fives are 35. We get 5 as the remainder, making this as 50. And 7 sevens are 49. We get 1 as the remainder, and this becomes 10. As you can see, we started with 10, and again we are at the same 10 again. So this is also another example of a rational number whose decimal expansion, or the division, never ends, and these digits 1, 4, 2, 8, 5, 7 keeps on repeating again and again. Before we go any further, just a quick recap of classification of numbers. Let's say this is our number line, and we have numbers starting from 0 and going up to positive infinity on one side. We also have numbers starting from -1 going up to negative infinity on the other side of 0. The numbers that start from 1 and go up to positive infinity are our natural numbers, represented with symbol n. They are also called counting numbers or countable numbers. Whole numbers are the ones that start from 0 and go up to positive infinity. Whole numbers are represented with symbol W, and as we can see, whole numbers contain all the natural numbers and additionally 0. So whole numbers is a superset of natural numbers. In other words, natural numbers is a subset of whole numbers. Integers range from negative infinity to positive infinity. So they contain all the whole numbers and in effect contain all the natural numbers as well. Additionally, integers include all the negative numbers as well. So it ranges from negative infinity to positive infinity, and it is represented with symbol Z. So integers is a superset of whole numbers and obviously natural numbers, and these two are subsets of integers. Numbers are not only are the ones that are represented on the number line. Between any two numbers, be it 3 and 4, 7 and 8, or -4 and -5, there are infinitely many numbers, fractional numbers. And all those fractional numbers, some of them can be represented in the P by Q form, and some of them cannot be represented in P by Q form. So if we take all those fractional numbers which can be represented in the P by Q form and add to integers, then we get rational numbers represented with symbol Q. So rational numbers contain all the numbers ranging from negative infinity to positive infinity, that is integers, and the fractional numbers that can be represented in the P by Q form. And the numbers that cannot be represented in the P by Q form are irrational numbers. Here are a few examples of rational numbers. This is 1 by 10 in fraction form and 1.1 in decimal form. And this is an example 3 1 by 5 in fraction form and 3.2 in decimal form. Similarly, this is minus 3 8 by 10 in fraction form and minus 3.8 in decimal form. So rational numbers then becomes a superset of integers and in effect whole and natural numbers as well. And all the three are subsets of rational numbers. A question may come up when we hear that rational numbers are the ones that can be represented in P by Q form. Then how come the integers, the ones, twos, threes, and so on, and similarly the minus one, two, three, and so on, are in P by Q form? Well, they can be represented in P by Q form. Say, for example, let's take the example of 4. 4 can be written as 4 by 1 and also 8 by 2. Similarly, if we take minus 5 as an example, minus 5 can be written as minus 5 by 1 or minus 10 by 2 as an example, right? And it is the same for the rest of the integers as well. So rational numbers contain all the integers and in effect whole and natural numbers as well. And these three are the subsets of rational numbers. Let's try to put the classification of numbers from a different perspective. As we discussed just now, natural numbers start from 1 and go up to infinity. And it's a subset of whole numbers which start from 0 and go up to positive infinity, in effect contain all the natural numbers. And whole numbers become a part of integers, and integers contain negative numbers as well along with whole numbers. So integers range from negative infinity to positive infinity. Integers and all the numbers that can be represented in P by Q form make up rational numbers. And rational numbers along with irrational numbers together, they form real numbers. Real numbers is the all-encompassing or the superset of all the numbers that we know. So we have been seeing natural numbers, whole numbers, and integers so far. And we also have taken a look at some of the examples of rational numbers. And when it comes to irrational numbers, we can't find two numbers to put it in P by Q form to represent a irrational number. And hence, the only examples that we have are the ones that we have taken a look at earlier in the video, the pi's, root 2's, root 3's, etc. And the values for the practical purposes that we take of pi as 3.14
and root 2 as 1.414 are the approximate values, not the real values, because irrational numbers cannot be represented actually in p by q form, and their decimal expansion or the division in simple terms never ends. Lastly, this view is in the form of subset and superset kind of relationship. If you go from inside out, natural numbers are a subset of whole numbers, which in turn is a subset of integers, and integers is a subset of rational numbers, which in turn become a subset of real numbers. And when we come from outside in, real numbers is the superset of all the numbers that we know, and it's a superset to rational numbers, and rational numbers in turn is a superset of integers, and so on. Few important points on the operations between rational and irrational number from our 9th grade syllabus. The operations, addition, subtraction, multiplication, and division of a rational number and an irrational number is always irrational, except when the rational number involved is 0, and especially when it is in multiplication or with division, it produces different results. An irrational number, when multiplied with 0, yields 0, which is a rational number. And when 0, which is a rational number, divided by an irrational number, is always leads to 0. And when 0 is in the denominator, that operation is undefined. So except for these few cases, the operations between rational number and irrational number is always irrational. And when two irrational numbers are added, subtracted, multiplied, or divided, will be either rational or irrational depending on the numbers involved. These 2 points are important as we go further into the topic where we prove the irrationality of our irrational numbers. Our next topics are Euclid's division lemma, which is used to calculate HCF, and Fundamental Theorem of Arithmetic, which mainly deals with the prime factorization of numbers. And we did a lot of prime factorizations and also calculated HCFs and LCMs in our previous grades. But before going through these 2 topics, let's go through some fundamentals. Let's study the general divisibility rules and understand what are the similarities or differences between factors and prime factors. Also see what are co-primes and how they can simplify the calculations of HCFs and LCMs, and also see how to figure out the second highest factor of an even number as well as odd numbers. So these fundamentals will be helpful in understanding the Euclid's division lemma or fundamental theorem of arithmetic in bit more detail. If not for that, having a knowledge of these fundamentals is always going to be helpful in some other calculations or some other chapters, and they keep coming back again and again in some shape or form, time and again. So let's go through them before we see the Euclid division lemma and fundamental theorem of arithmetic. Let's see some general divisibility rules. We have already seen the divisibility rules of 2, 3, 4 up to 11 in our previous grades. These are some more divisibility rules. One important point to note here is that whenever we say divisibility, of two numbers, let us say x and y is completely dividing x. In other words, it is leaving remainder as 0 at some point of time during the division. That's what is the meaning of divisibility. The first rule says that if a number x is divisible by another number y, then x is divisible by each of the factors of y. What it means is that y is dividing x completely, leaving no remainder, or in other words, leaving 0 as the remainder. Then any factor of y can also divide x completely, leaving 0 as the remainder. The next rule, if a number x, if it is divisible by two co-prime numbers y and z individually, then x is divisible by their products y and z as well. So what it means is that y is dividing x completely individually, and so is z. If so, then x can be divided completely by the product of y and z. So what are co-prime numbers? The definition is two numbers having only one as the common factor are called co-prime numbers. These two rules are related. What they say is that if two given numbers x and y, if they are divisible by a number z, then their sum x plus y as well as the difference x minus y is also divisible by z. Let's see all these rules with few examples now. Here is our first rule, which says that if a number x is divisible by another number y, then each of the factors of y will also be able to divide x. So let's pick a number x, 12, and let's pick another number y which can divide x completely. So let's pick y as 6. So 12 divided by 6 will give us 2 as the quotient and 0 as the remainder. Now let's check the factors of 6. Are they able to divide completely the number 12? So the factors of 6 are 2 and 3. Of course, 1 is a factor of every number, so let's ignore 1 for the moment, because 1 can divide any number completely. So 12 divided by 2, the first factor of 6, will give us 6 as the quotient and 0 as the remainder. And 12 divided by 3 will give us 4 as the quotient and 0 as the remainder. So both 2 and 3, which are the factors of 6, are also able to divide the same number 12 completely, leaving 0 as the remainder. Now let's pick another number, say 50 as our x, and another number y which can divide 50 completely. Let's pick y as 10. So 50 divided by 10 will give us 5 as the quotient and 0 as the remainder. So 10 is completely dividing 50. Now what are the factors of 10? 2 and 5 are the factors of 10. Now let's see, 2 and 5 can also divide 50. So 50 divided by 2
will give us 25 as the quotient and 0 as the remainder, and 50 divided by 5 will give us 10 as the quotient and 0 as the remainder. So these are few examples of this rule. Please try with few more appropriate numbers. Pick one x and another number y which can completely divide x, and try with few more numbers, and then see the factors of whatever number you choose as y. The factors of that number are able to divide x, provided y can completely divide x. This is our second rule. If a number x is divisible by two co-prime numbers y and z individually, that means that y can divide x completely and so is z, which can completely divide x, then x is divisible by their product. So x is divisible by the product of y and z. And what are co-prime numbers? Co-prime numbers are two numbers which have only 1 as the common factor. So let's take few examples. Say, let's pick a number 30. 30 can be divided by both 3 and 5. So we know that 30 divided by 3 is 10 and 30 divided by 5 is 6. So 30 can also be divided by the product of these two co-prime numbers, 3 and 5, which is nothing but 15. So if 30 gets divided by the product of the two co-prime numbers, 3 and 5, we get 2 as the quotient and 0 as the remainder. So the product of the two co-prime numbers is also able to divide the same number, provided individually the two co-primes 3 and 5 can divide 30. Let's take another example, 50. 50 can be divided by both 2 and 5, which is another pair of co-prime numbers. So we know 50 divided by 2 is 25 and 50 divided by 5 is 10. So what is the product of 2 and 5, which is 10? So 50. Now let's see, can it be divided with the product of these two co-prime numbers, 2 into 5, which is 10. And 50 divided by 10 is 5 as the quotient and 0 as the remainder. So 10 can also divide 50, and 10 is the product of these two co-prime numbers. Let's take another example, say 100. 100 can be divisible by two co-prime numbers, 4 and 5. 100 divided by 4 is 25 and 100 divided by 5 is 20, and the product 4 into 5, 20, should also be able to divide 100. So 100 divided by 4 into 5, which is 20. So 100 by 20, as we know, is 5, leaving 0 as the remainder. So 20 can also divide 100, which is the product of these two co-prime numbers. So please try with few more examples, picking up appropriate numbers and corresponding co-prime numbers, and then see if they can divide the y and z, the two
prime numbers, if they are able to divide x, then their product should also be able to divide x. Here are the next two rules which are similar. So what they say is that if two given numbers x and y are divisible by another number z, then their sum x plus y as well as the difference x minus y is also divisible by z. So let's pick few numbers. Let's say 18 and 6. And let's pick a number which can divide both these numbers. Say 3. 3 can divide both 18 as well as 6. So 18 plus 6, which is 24, is also divisible by 3. And we get 8 as the quotient and 0 as the remainder. And 18 minus 6 is also divisible by 3, which is 18 minus 6 is 12, and 12 can be divided by 3. We get 4 as the quotient and 0 as the remainder. Similarly, let's take another example, say 14 and 35. 7 can divide both 14 and 35. Now let's see 14 plus 35. Is it also divisible by 7? 14 plus 35 is 49, and 49 indeed can be divided by 7. We get 7 as the quotient and 0 as the remainder. Not only that, if we subtract one number from the other, say 14 minus 35, can it be divided by 7? Let's see. 14 minus 35 is minus 21. Yes, indeed, minus 21 can be divided by 7, and we get minus 3 as the quotient and 0 as the remainder. So the sum and difference of the numbers can also be divided by the same numbers, provided it can individually divide these two numbers. So here are a few examples for these two rules. Please try picking up appropriate numbers and a number that can divide both the numbers, and then see if their sum and difference can also be divided by the third number. We have seen some of the general divisibility rules and how do they work. Now let's see two more important terms when it comes to divisibility, that are factors and prime factors. Let's see what are the similarities and differences between the factors and prime factors. So a factor is defined as a number that divides another number exactly, completely, leaving no remainder, or in other words, 0 as the remainder. So what is a prime factor? Prime factor is also a factor. It's just that it happens to be a prime number. So prime factor is also a number, a prime number, that divides another number exactly or completely, leaving no remainder or 0 as the remainder. Let's see both of them with few examples. Let's pick one example, 12. So what are the numbers that can completely divide 12, leaving
0 as the remainder. So we know that 1 can divide 12, 2, 3, 4, 6 and 12. Every number is a factor of itself, so 12 is a factor of itself and it can divide itself completely, leaving 0 as the remainder, and so are these numbers as well. So as you can see, these are a mix of both prime numbers and composite numbers. 2, 3 are our prime numbers and 4, 6, 12 are composite numbers. So it's a mix of both prime numbers as well as composite numbers which can divide 12 completely, leaving no remainder or 0 as the remainder. But when we say prime factor of 12, these are only two, that are 2 and 3 are the only prime factors of 12. So in case of a normal factor, we can get back 12 in many different ways. Say for example, 3 into 4 is 12, which is a combination of a prime number and a composite number. 6 and 2, again a combination of a prime number and composite number, we can get 12. Here in this case, we can get back 12 only using prime numbers, that is 2 into 2 into 3. 2 into 2, 4, 4 into 3, 12. So these are the differences or similarities between factors and prime factors. Factors can be any number, be it prime number or composite number, that is able to divide another number completely, leaving 0 as the remainder. Whereas a prime factor of a number or only contains prime numbers. Let's take another example, say 20. So what are the numbers that can divide 20 which can leave no remainder when divided? These are 1, 2, 4, 5 and 10 and of course 20. 20 can divide itself, as every number is a factor of itself, and so are all these numbers 2, 4, 5, 10, and one can divide any number completely and it's a factor of any number. So again, here we see a mix of both prime numbers as well as composite numbers being the factors of 20. 2 and 5 are the prime numbers, whereas 4, 10 and 20 itself are the composite numbers. So when it comes to 20 prime factors, so only 2 and 5 are the prime factors of 20, whereas we can get back 20 here in many different ways using a combination of prime numbers as well as composite numbers. So for example, 2 into 10 is equal to 20. It's a combination of a prime number 2 and a composite number 10. And 4 into 5 is also 20. Again, a combination of a composite number and prime number. And of course, we can also write 1 into 20 is 20. So these are the different ways of getting 20. But whereas when it comes to getting 20 using prime numbers, it only has to be 2 into 2 into 5. 2 into 2 is 4. 4 into 5 is 20. So Here are the examples of factors and prime factors. Please try with few more numbers and try to identify what can be a normal factor of a particular number and what are its prime factors. Here are few more points related to factors. If you pick a even number, the highest factor apart from itself is half of that number. So half of that number would be the second highest factor. So let's take a combination of 6 and 12 here. 12 can divide itself because every number is a factor of itself. But if you keep it aside, the second highest factor of 12 would be half of 12, which is 6. Similarly, for 16, 8 would be the second highest factor, and for 92, 46 would be the next or second highest factor, and so is 50 for 100. If you pick a odd number, the highest factor, apart from the number itself, of course, is less than half of that number. So that would become the second highest factor. So it is calculated using this formula. The odd number that has been picked when divided by the smallest prime factor of that odd number gives us the second highest factor. So here are a few examples. Say 15. The smallest prime factor that can divide 15 is 3. So 15 divided by 3 will give us 5. Similarly, 27, the smallest prime factor which can divide 27 is 3. So 27 divided by 3 gives us 9. And similarly, these two examples. 35, the smallest prime factor that can divide 35 is 5. So when 35 is divided by 5, we get 7 as the second highest factor for 35. And for 57, 3 would be the smallest prime factor, and when you divide 57 with 3, you get 19, which happens to be the second highest factor of the odd number 57. Now let's take a brief look at Euclid's division lemma. What this theorem says is that given two positive integers a and b, there exist two unique integers q and r satisfying the condition a is equal to b into q plus r, where r is greater than or equal to 0, but it is always going to be less than b. The theorem in its simplest form can be written as dividend is equal to divisor into quotient plus remainder. So what is the dividend? Dividend is the number that is getting divided. Divisor is the number that is dividing the dividend. So when the division happens, we get some quotient and some remainder. In our case, A is our dividend, which is getting divided. B is the divisor, which is dividing the dividend. Q is the quotient and R is the remainder. So the important point to note here is that when the remainder is 0, then divisor is a factor of dividend. And if the remainder is a non-zero number, then divisor is not a factor of dividend. Let's see a few examples. 9 divided by 2 can be written as 9 is equal to 2 into 4 plus 1. 2 into 4 is 8. 8 plus 1, 9. So here the remainder is 1. So 2 is not a factor of 9. But if the same 9 divided by 3 will leave a remainder 0, so 3 is a factor of 9. Another example, 24 by 5. can be written as 24 is equal to 5 into 4 plus 4. 5 into 4 is 20. 20 plus 4, 24. Here there is a non-zero remainder 4. So 5 is not a factor of 24. And the same 24 when divided with 3 will give us 8 as the quotient and 0 as the remainder. So because the remainder is 0 here, 3 is a factor of 24. Another example, 36 by 7 can be written as 36 is equal to 7 into 5 plus 1. 7 into 5 is 35 plus 1, 36. So there is a non-zero remainder here, 1. So 7 is not a factor of 36. And the same 36 when divided with 6 will give us 0 as the remainder, as 6 into 6 is directly equal to 36. So 0 is the remainder. So in this case 6 is a factor of 36. So in all these cases, what we can notice is that the remainder is always going to be less than the divisor. Here the remainder is 1, divisor is 2, so 1 is less than 2. Similarly here we have 4 as the remainder, 5 is our divisor, so the remainder 4 is less than the divisor 5. Similarly 1, which is the remainder, is less than 7, which is the divisor. So in summary, when the remainder is 0, then the divisor is a perfect factor of dividend. That means that it can completely divide the number. And when the remainder is a non-zero number, then the divisor is not a factor of dividend. Now that we have some idea of the general divisibility rules and what are factors and prime factors, let's get into Fundamental Theorem of Arithmetic. This theorem is all about prime factorization of a composite number, which we have learned in the previous grades. So what this theorem says is that every composite number can be expressed or factorized as a product of primes. That means prime numbers. And when we do the prime factorization, the combination that comes up for this composite number is unique, apart from the order in which the prime factors occur. In simple terms, when we do a prime factorization of a composite number, the combination of the prime factors that come up is unique to every composite number, and no two composite numbers will have the same combination of prime factors. So let's take few examples and see. Let's pick up 90. We can start the prime factorization of 90 starting with 2, and we get a combination of 2, 3, 3, 5. We can also do the prime factorization of 90 in two other different ways. We can as well start with 3, and we get 3, 3, 2, 5 as the combination now. And with 5, we get 5, 3, 3, 2. But if we observe, if we write the prime factors in the increasing order, all of them turn out to be 2, 3, 3, 5. In whichever way you start the prime factorization. Now let's pick up another number, 315. We can start with 3 and we get a combination of 3, 3, 5, 7 as the prime factors. And we can also do in two other ways. We can start with 5 and 7 and we get 5, 3, 3, 7 or 7, 3, 3, 5. But if we write in the order, all of them are unique in the sense that they all are 3, 3, 5, 7. So that's what the theorem says, that every composite number can be expressed as a product of primes,
the prime numbers, and this factorization is unique for every composite number, in whichever way we start the prime factorization. Now it is time for us to take a look at HCF, highest common factor, and LCM, least common multiple of two or more numbers. We already know how to calculate HCF and LCM by using prime factorization, which we learned in the previous classes. Here are some unique cases where we can find the HCF and LCM a bit more easily rather than doing the prime factorization all the way. But before that, let's keep in mind one important point about factors and multiples. Every number is a factor of itself, and every number is also a multiple of itself. So with that in mind, let's take two numbers, x and y, and if x happens to be a factor of y, then HCF is x and LCM is y. Said in other words, if y is a multiple of x, then HCF is x and LCM is y. Let's take a look at few examples. So here is a case of 6 and 12. 6 is a factor of itself because every number is a factor of itself, and 6 is also a factor of 12. So between two of them, the highest common factor would be 6. And when it comes to LCM, 12 is a multiple of itself because every number is a multiple of itself. So 12 is multiple of itself, and it's also a multiple of 6. So between two of them, LCM would be 12. Similarly, 4 is a factor of itself as well as it is a factor of 16. So between two of them, HCF would be 4. And when it comes to LCM, 16 is a multiple of itself as well as it is a multiple of 4. So between two of them, LCM would be 16. Here are a few more examples for you to go through, and please try with few other such combinations where one number is a factor of the other number, or in other words, the second number is a multiple of first number. Let's take few more cases of HCF and LCM and see if there are any other simple ways. This time let's pick four numbers. Here is our first set: 6, 12, 24 and 48. And 6 is a factor of itself, and it is also a factor of 12, 24 and 48. So between them, 6 then would become the highest common factor. And when it comes to LCM, 48 happens to be the multiple of 6, 12, 24. Of course, it's a multiple of itself. So between them, 48 then will become the LCM. It's a pretty straightforward case, just as the two numbers examples that we have seen a moment ago. Now let's take another set, this time with a slight variation. 6, 12, 18 and 48 is now our set. 6 is a factor of itself, and it's also a factor of 12, 18 and 48. So among them, then 6 would be the highest common factor. When it comes to LCM, 48 is a multiple of itself, and it's also a multiple of 6 and 12. But it is not a multiple of 18. So in this case, since 48 is a multiple of itself and it's also a multiple of 6 and 12, all that we need to do is to calculate the LCM between these two numbers, and we get 144 as the LCM. We don't need to calculate for all the numbers. Whichever numbers for which the largest number is not a multiple, only between those two numbers we have to take the LCM. And another set, 6, 9, 18 and 48. In this case, 6 is a factor of itself, but it is not a factor of 9, but it's a factor of 18 and 48. So 6 is a factor of 18 and 48. So all that we need to do is to take the HCF between 6 and 9, which happens to be 3. And when it comes to LCM, 48 is a multiple of 6, but it is not a multiple of 9 and 18. So in this case, the second number happens to be a factor of 18, or 18 happens to be the multiple of 9. So in this case, all that we need to do is, since 6 is a factor of 48, or in other words, 48 is a multiple of 6 and 18 is a multiple of 9, again we need to only calculate the LCM between 18 and 48, and we get again 144 as the LCM for these numbers. So whenever the group of numbers happens to be factors or multiples of each other, if we keep these points in mind, it may save some amount of time for you to calculate HCF and LCM. And please try with different combinations of numbers and actually do the prime factorization and see whether these points that we discussed for 2 numbers and these examples where we have taken 4 numbers, for these indeed we are getting the results using the points that we have discussed. The methods we have seen so far for calculating the HCF and LCM work for smaller numbers, where we can easily figure out if one of the numbers is a factor of the rest of the numbers, then that would become the HCF. And if one of the numbers turns out to be the multiple of rest of the numbers, then that number would become the LCM of that group of numbers. But what if we have to do HCF and LCM for large numbers? Let's see few unique cases now to handle HCF and LCM for larger numbers. This method works if the numbers involved have something in common among them. Let's pick 3 numbers A, B, C, and let's say K is a common factor among them. And if we pull K as a common factor, then the numbers A, B, C would be reduced to A by K, B by K, and C by K, which are relatively smaller numbers than the actual numbers A, B, C. And calculating the HCF or LCM of the smaller numbers would be relatively easy. Let's take few examples and see. This is the first case, 120 and 180. And as we can see, 10 is a common factor between 120 and 180. And if we take 10 as a common factor out, then 120 would be reduced to 12 and 180 would be reduced to 18. It's like 120 by 10 is 12 and 180 by 10 is 18. And these are relatively smaller numbers than the actual numbers 120 and 180. And calculating the HCF or LCM for 12 and 18 would be relatively easy than calculating the HCF and LCM of 120 and 180. Imagine the amount of time we have to spend for doing the prime factorization of 120 and 180. So once we calculate the HCF of the smaller numbers 12 and 18, it turns out to be 6. Just multiply with the common factor that we have taken out. So 10 is the common factor we have taken out, and HCF of 12 and 18 is 6. So 10 into 6 will give us 60, and 60 would be the HCF of 120 and 180. Similarly, these two examples, 45 and 75, 15 would be the common factor for 45 and 75, and if we take out 15 as a common factor, then the numbers would be reduced to 3 and 5. 45 by 15 is 3 and 75 by 15 is 5. So calculating HCF of 3 and 5 would be relatively easy than calculating the HCF for 45 and 75 using prime factorization. So HCF of 3 and 5 would be 1 only. Then multiply that with the common factor that is taken out. So 15 into 1 is equal to 15. The 15 would be now the HCF of 45 and 75. Similarly, another example for you to go through. Same is the case with LCM as well. We can take whatever common factor among the numbers and then take that common factor out. The numbers would be reduced to smaller numbers, and calculating the LCM of smaller numbers would be relatively easy than calculating the LCM of bigger numbers ABC. So again, 120, 180, 10 is a common factor. So if we take 10 out, the numbers would be reduced to 12 and 18. And LCM of 12 and 18 would be 36. So multiply that 36 with the common factor that is taken out, 10. So the LCM would be 360 for 120 and 180. Similarly, 15 is a common factor between 45 and 75. And if we take that out, the numbers would be 3 and 5. And the LCM of 3 and 5 is 15. So multiply the LCM of 3 and 5, which is 15, with the factor that we have taken out, 15. So 15 into 15 is 225. Similarly, one more example. Please try at your end with few other combination of A, B and C, or for that matter, you can take any number of numbers, 2, 3, 4, any number. And the only condition is that if they have something in common, we can take that out and calculate the HCF of or LCM of those numbers, and then multiply with the common factor that is taken out. So this surely should save us some time. As we know, calculating the HCF or LCM using prime factorization is a little time consuming process, and if we can encounter these kind of numbers, then taking the k as common out and reducing the numbers to smaller numbers and then calculating the HCF or LCM would be relatively easy and quicker. One important point to note here is that when we take the common factor out between A, B and C, it's not that we have to waste time in identifying the perfect common factor or the largest common factor to pull out in one attempt. We can do it iteratively also in successive attempts. So let's go back to the example of 120 and 180 and calculating HCF. We can easily spot that 10 is a common factor between 120 and 180 because 120 is 12 into 10 and 180 is 18 into 10. So 10 would be the first factor we can immediately figure out. So once we take that common factor out, the numbers would be reduced to 12 and 18. 120 by 10
is 12 and 180 by 10 is 18. Once done, if there is any common factor that can be pulled out, we can pull that out in the next attempt also. As we can see, 6 would be the common factor between 12 and 18, and we can pull that out as well along with 10 in the next attempt. And now the numbers would be reduced to 2 and 3. 12 divided by 6 is 2 and 18 divided by 6 is 3. And calculating the HCF of these even smaller numbers would be relatively easy. And the HCF of 2 and 3 is 1 because they are co-prime numbers. And then multiply that with whatever is the common factor or factors that we have pulled out. In this case, 10, 6 is what we pulled out and HCF is 1. So 10 into 6 into 1 gives us 60, which would be the HCF of 120 and 180. Same is the case with LCM also. It's not that we need to pull out the largest common factor in one go. We can pull them iteratively in successive attempts to make the numbers as small as possible, and calculating the HCF or LCM of those smaller numbers would be relatively easy. Maybe save some time for us. Lastly, this is an example where we have 3 numbers, and as mentioned before, it is not just limited to 3 numbers or 2 numbers. We can take as many numbers as we want. Yeah, and as long as they have something in common between all of them, we can keep pulling them out. There are times where we can come across co-primes while calculating HCF, and the HCF of co-primes is always going to be 1. So in a given set, if any 2 of the numbers are co-prime, then the HCF of entire set then will become 1. Here are a few examples: 3, 5, 10 and 15. So though 3 is a factor of 15, 5 is a factor of 10 as well as 15, we need not calculate the prime factorization and then further calculate HCF. 3 and 5 are co-primes and their highest common factor is 1, then the entire set's highest common factor would be 1. Here is another example: 4 and 9. Though 4 is a factor of 16 and 9 is a factor of 18, we need not do the prime factorization and then calculate HCF. 4 and 9, if we can spot that as co-primes, then the HCF of entire group of numbers will become 1. Similarly, here 4 and 25 are co-primes. So though 5 is a factor of 15, 25 and 50, we need not further look, as 4 and 25 are co-primes, then the HCF of entire set would be 1. Another 2 example, here 5 and 12 are co-primes, so the HCF of entire set is 1. And here 8 and 27 are co-primes, so HCF of this group of numbers is 1. And similarly here 14 and 25 are co-primes. So this method works whether we have 2 numbers, 3 numbers, 4 numbers or any number of numbers, as long as 2 of them are co-primes and we could spot them, then we further need not calculate the HCF using prime factorization or other methods. The HCF immediately will become 1. Another important point is that any 2 consecutive numbers are co-primes. So be it, as an example, 8 and 9, 21 and 22, 42 and 43, 51, 52, 89, 90. Any 2 consecutive numbers are always going to be co-primes, and if so,
their HCF would become 1. So in a given set of numbers, if there are two consecutive numbers, then the HCF of entire set will become 1. So here is one example: 12, 18, 24 and 25. 24 and 25 are consecutive numbers, so they are co-primes, and the HCF of the entire set will become 1. Here 98 and 99 are consecutive numbers, so co-primes. HCF of the entire set then will become 1. Here 64 and 65 are consecutive numbers, so become co-primes, making the HCF of entire set to be 1. Here 9 and 10 are co-primes as they are consecutive numbers, so HCF of the entire set will become 1. And here 5 and 6 are consecutive numbers and co-primes, so HCF of the entire set is going to be 1. In general, if we encounter a series of consecutive numbers, their HCF is always going to be 1, as if you take any two pairs, they are going to be consecutive numbers and co-primes. So HCF of the entire set is going to be 1. One important point to note here is that consecutive numbers are always co-primes anyways, but all the co-primes need not be consecutive numbers. So if you take the few of the examples here, 3 and 5 are not consecutive, but still they are co-prime because the highest common factor that can come between 3 and 5 is 1, so they are co-prime. Similarly, 4 and 9 are surely not consecutive numbers, but they are still co-prime. Similarly, 4 and 25, 5 and 12, 8 and 27, and 14 and 25, they are definitely not consecutive numbers, but they are still co-primes because the highest common factor between them is 1. So consecutive numbers are co-primes, but the important point to note here is that co-primes need not always be consecutive numbers. When it comes to LCM of co-prime numbers, it can easily work for two numbers, two co-primes, where we simply have to multiply to get the LCM. So if A and B are co-prime, then the LCM of those two numbers would be product of those two numbers A and B. When it comes to three or more consecutive numbers, then it involves few more checks, so it may eat up time. And so it is easier to use the methods that we saw a few moments ago, or the prime factorization method as the last resort. So for two numbers, if they are co-prime, we can easily calculate by multiplying the numbers together to get the LCM. Three or more numbers, better to go with some other method, or as a last resort, prime factorization method. And one final point related to HCF and LCM of two numbers is that there is a relation given as HCF of those two numbers multiplied with LCM of those two numbers is equal to product of those two numbers. This is a general equation, works for any two A and B's. We just saw few of the variations when it comes to calculating the HCF and LCM, some unique cases. Irrespective of all those conditions, for any two A and B, if we calculate HCF and LCM and multiply, that would be always be equal to the product of those two numbers themselves, A and B. The same relationship can be written in two other ways. HCF of those two numbers is equal to the product of those two numbers divided by LCM, and LCM of those two numbers is given as the product of those two numbers divided by HCF. This is a general equation, and when we see in the context of co-prime numbers, let's say A and B are co-prime now. So LCM of co-prime numbers, which we just saw a few moments ago, is equal to the product of those two numbers. So it would be A times B or A into B. So A into B divided by A into B will give us 1, which is nothing but HCF. And we did say that if A and B are co-prime numbers, its HCF would be 1. And similarly, when A and B are two co-prime numbers, HCF would be 1. So A times B or A into B divided by 1 is equal to LCM. And we did say that LCM of those two numbers, especially when they are co-primes, is equal to the product of those two numbers. Because A times B or A into B divided by 1, which is the HCF of two co-prime numbers, A into B divided by 1 is equal to A into B. And LCM of A and B would then be equal to A into B. And that's what we just discussed a few moments ago. Now let's try to put together a summary of all that we discussed about HCF and LCM as a general approach. For HCF, take a look at the numbers. If you can spot any two numbers being consecutive, or if not consecutive co-prime numbers, then HCF of the entire set would be 1. If this is not the case, then take a look at the smallest number. If it is a factor of rest of the numbers, then HCF of the entire set would be smallest number. Even if this is also not the case and the numbers are large, try using the common factor method that we discussed a few moments ago. For LCM, as we discussed, the consecutive or co-prime method will work only for two numbers. So if they are either consecutive or if not consecutive co-prime numbers, then LCM would be product of the numbers. And for three or more numbers, better use the other method that we discussed, or as a last resort, the traditional prime factorization method. If the numbers are not consecutive or co-prime, then take a look at the largest number. If it is a multiple of the rest of the numbers, then LCM would be the largest number. And even if this is not the case, and if the numbers turn out to be very large, then try using the common factor method. So these are few of the methods apart from the Euclid division lemma, which is used to calculate HCF. These are the methods that we can use for calculating HCF and LCM. Hopefully, this will save some of our time for calculating HCF and LCM.
One final point in the general approach for calculating HCF and LCM. If in a group of n numbers, if two or more numbers are distinct primes, then the HCF of the entire set of n numbers would be 1. What do you mean by prime? Prime numbers. And what do you mean by distinct? Different prime numbers. At least two of them should be different. It can be more also, but if at least two numbers in the set of n numbers are distinct primes or different primes, then the HCF of the entire set of numbers is 1. Here are a couple of examples, 3, 7 and 21. 3 and 7 are two distinct primes or different primes. So the HCF of this set of numbers is 1. As you can see here, 7 is a factor of 21. It can divide 21. But between 3 and 7, because they are prime numbers, the only common factor would be 1. So the HCF of entire set of numbers would be 1. Another example, 2, 20, 30, 11 and 50. As you can see, 2 and 11 are distinct primes or different primes. In this case also, the HCF of the entire set of numbers is 1. As you can see, 2 can divide 20, 30 as well as 50 also, but 2 cannot divide 11. So 2 and 11 are prime numbers, and the only common factor between any two prime numbers is 1. So the HCF of entire set of n numbers would be 1. Rather, this set of numbers would be 1. Or we can take any number of numbers. The number of numbers that we take doesn't matter, as long as two of them are distinct primes. The HCF of entire set of n numbers that we have taken would be 1. Now coming to LCM, if in a group of n numbers, if the numbers are distinct primes or different primes, all of them, then the LCM of the set of n numbers would be product of the numbers. So here are two examples, 2, 3, 5. All of them are distinct primes or different primes. Then the LCM of this set of numbers would be simply the product of numbers, 2, 3, 5, 2 into 3 into 5. Similarly, another example, 3, 7, 11, 13. So all of them are distinct primes or different primes. So the LCM of this set of numbers would also be product of numbers, 3 into 7 into 11 into 13. So we can have more numbers also. We can take any number of numbers as long as all of them are distinct primes. Then we need not do the prime factorization or do other methods. We simply have to multiply the numbers. In this case also, you can take any number of numbers as long as two of them turn out to be distinct primes. Then we need not do the complete prime factorizations and other methods to calculate the HCF. We can simply finalize the HCF of the entire set of numbers as 1. So we discussed quite a number of unique cases for calculating HCF and LCM, the simpler methods. So try all of them and also cross-check the results by doing the traditional prime factorization or other methods which you may be using, and see if the results are matching between the simpler methods that we discussed here and with the traditional methods. See if the results are matching. Now it is time for us to get into proving irrationality of certain numbers. And this is the theorem that helps us in proving irrationality. So what is this theorem saying? Let P be a prime number, and if P can divide a square number, a square, P can also divide the root of a square, that is a, where a is a positive integer. So let the prime factorization of a be P1 into P2 into P3 up to Pn. Each one of them are the prime factors of a. And we know that any one of the P1, P2 up to Pn can divide a because they are the prime factors of a. Then what is a square? A square is nothing but a into a. So substituting the product of the prime factors, we get P1 into P2 into P3 up to Pn multiplied by the same set, because we are multiplying a into a here. And it is given in the theorem that P can divide a square. So what is a square? We just calculated the product of the prime factors of a multiplied by the same, because a into a is a square. So substituting this value for a square divided by p, then given that p divides a square, then this division must result in remainder being 0. For this to happen, p has to cut any one of them, either p1 or p2 or p3 or pn. Of course, it can do the same here as well. If it can cut p1 here, it can also cut p1 here. Of course, one of them. And if it can cut p2 here, it can cut p2 here as well. One of them. So obviously, then p would be one of this set of numbers. Either it could be p1 or p2 or p3, one of them. So p is one of the prime factors of p1, p2 up to pn, one of them. And what are these prime factors? They are the prime factors of a. Each one of them can divide a because they are the prime factors of a. And p being one of the p1, p2 up to pn, p can also divide a. So in simplest term, if a prime number can divide a square number, the prime number can also divide the root of that square number. In this case, the square number is a square, the root of that a square is a. Now let us see with few examples. Let us try to understand the theorem with a couple of examples. In simplest term, what this theorem is saying is, if a prime number p, if it can divide some square number a square, then p can also divide the root of a square, which is a. So let us pick up some square number a square, and let's pick up some p prime number which can divide the square number. So let's pick up our a square as 36 and the prime number p as 3, which can divide the square number 36. So 3 can divide 36 and we get 12 as the quotient and 0 as the remainder. Now if a square is 36, what is a? Our a would be 6 because 6 into 6 is 36. So the root of a square is a, which is nothing but 6 in our case. And the prime number p, which is 3 in our case, can also divide the a, which is our 6 here, which is root of our a square. So 3 can divide 6, which is our a here, and gives us 2 as the quotient and 0 as the remainder. The reason why this happens is that in the prime factorization form, let's get into the prime factorization form and see. A square is 36, which is nothing but 6 into 6. And the prime factors of 6 are 2 and 3. So 6 into 6 is nothing but 2 into 3 into 2 into 3. So the prime number that we picked up for this case is 3. So 3 is cutting one of the 3's here. It can cut one of them. So either this 3 or this 3 doesn't matter. It can cut one of them. So if 3 is cutting 3, what remains is 2 into 2, 4, 4 into 3, 12. And that is what we got as the quotient here. So what is a? A is nothing but 6 in our case, because root of a square 36 is 6. So our a is 6 here, which is again composed of the same 2 and 3. So 3 can cut this 3. Our prime number p that we selected here is 3. So 3 can cut 3, and what remains is 2, and that is what we got as the quotient here. So that is the meaning of this theorem. If a p, prime number p, can divide a square, it can divide a as well. Now let us see with another example. Let's pick now our a square as 625 and our prime number p as 5. 5 can divide 625 and we get 125 as the quotient and 0 as the remainder. And if a square is 625, what is our a? Root of a square, which is 625, is 25. So root of a square a is 25 in our case. So 5 can also divide our a, 25 here, and gives us 5 as the quotient and 0 as the remainder. So getting into the prime factorization form, our a square is 625, which is nothing but 25 into 25. And in prime factorization form, it is 5 into 5 into 5 into 5, because the prime factors of 25 are 5 and 5. So 25 into 25 is 5 into 5 into 5 into 5. So the prime number p, 5, if it is dividing a square, that means that it is cutting one of the 5s here. So it can cut any one of the 5, only one 5. So let's say prime number 5 is cutting this 5. What remains is 5 into 5, 25. 25 into 5, 125, and that is what we got as the quotient here. And if a square is 625, our a is 25, which is nothing but the same 5 and 5, one of the 5 and 5s here. So 5 can cut 5. The prime number 5 can cut one of the 5s here. And if it is cutting 5, what remains is 5, and that is what we got as the quotient here. So in summary, as we discussed, if a prime number p, if it can divide some square number, it can also divide the root of a square, which is a. And this principle is used to prove the irrationality of numbers, which we are going to see now. Now let us start proving root 2 to be an irrational number. The method that we are going to use is proof by contradiction method. This method involves starting with an assumption which is quite opposite to what we are trying to prove, and finally proving that our initial assumption is wrong. Here we are trying to prove root 2 to be irrational. So on the contrary, let's assume that root 2 is a rational number. And in order for root 2 to be a rational number, it must be expressed in p by q form, as we have seen earlier in the video. So let's pick r and s as the numbers instead of p and q as per the book. So root 2 can then be expressed as r by s. And if it is not in the simplest form, reduce it to simplest form, a by b. And in this simplest form, a and b would be co-primes. And we know that when two numbers are co-prime, their HCF would always be 1 and only 1. They have only 1 as the highest common factor and no other number. So if we rearrange root 2 is equal to a by b, we get b root 2 is equal to a, and squaring on both sides, we get 2b square is equal to a square. Let's take this as equation 1. So here a square is expressed as 2b square, that is 2 into b into b. So it is expressed in the factor form where 2 and b are factors of a square. So 2 can divide a square. And by theorem 1.3, if 2 can divide a square, it can also divide a. So when a gets divided with 2, we get some quotient c with remainder being 0. And if we rearrange a by 2 is equal to c, we get a is equal to 2c. So let's go back to our equation 1, 2b square is equal to a square. And now substitute a is equal to 2c in our equation. And substituting 2c for a in equation 1, we get 2b square is equal to 2c whole square, that is equal to 4c square. And if we can cut 2 and 4, we get b square is equal to 2c square. Now here b square is expressed as 2c square, that is 2 into c into c. So both 2 and c are factors of b square. So 2 can divide b square. And if so, 2 can also divide b. So what is happened here is that 2 ended up as a factor, common factor for both a and b. As we have seen, 2 was dividing a earlier, and now 2 also is dividing b. So 2 becomes a common factor of both a and b. But we started off saying that a and b are coprimes, and they should have only one as the common factor, highest common factor. But here we are getting 2 as the common factor. So this contradicts the fact that a and b have no common factors other than 1, as they are coprimes. So this contradiction is due to the fact that our initial assumption was incorrect, that root 2 is rational. Hence, we conclude that root 2 is irrational. It is the same method we can use to prove irrationality of root 3, 5, 6 and so on for all the numbers, individual numbers that are shown here. Of course, the same methodology works for proving irrationality of any individual numbers. Now we know how to prove an individual number to be irrational. Now let's see how to prove a combination of a rational number and irrational number to be irrational. Here is a number 5, which is a rational number, and root 3, as we know, is irrational. And earlier in the video, we saw that any operation between a rational number and irrational number is always irrational. So 5 is rational and root 3 is irrational, and root 3 is being subtracted from 5, which is surely an irrational number. And that is what we need to prove now. The method that we are going to use is the same proof by contradiction method that we used to prove root 2 to be rational. So let's start with the assumption that 5 minus root 3 is rational. And for it to be rational, there has to be two integers r and s not being equal to 0, so that we can express 5 minus root 3 as r by s. And if it is not in the simplest form, bring it to the simplest form a and b. And in this form, a and b would be coprimes. So rearranging the equation, 5 minus root 3 is equal to a by b. If you bring a by b over here, it will become 5 minus a by b. And if you send minus root 3 over to the right side, it will become positive root 3. So this is what we get after rearranging. 5 minus a by b is equal to root 3.
rewriting, we get root 3 is equal to 5 minus a by b. And we know a by b are integers. So 5 minus a by b is going to be a rational number. And if so, we have root 3 on the left hand side. So if the right hand side is rational, left hand side also has to be rational. So then that makes root 3 is rational. But this contradicts the fact that root 3 is irrational. So this contradiction has arisen because of our incorrect assumption that 5 minus root 3 is rational. So we conclude that 5 minus root 3 is irrational. Not only 5 minus root 3, but we can also prove 5 plus root 3, 5 into root 3, 5 divided by root 3 to be irrational following the same process. And in general, we can prove any combination of a rational number and an irrational number to be rational, except when 0 is in multiplication or division, then they become rational. So except the multiplication case or division case with 0, any other combination of a rational number and irrational number, and be it any operation between them, addition, subtraction, multiplication and division, we can prove them to be irrational using the same methodology. The next case is a multiplication operation between a rational number and irrational number and proving it to be irrational. Here our rational number is 3 and irrational number is root 2, and they are in multiplication with each other. And as we have seen and discussed earlier, any operation between a rational number and irrational number is always going to be irrational, except few cases when they are in multiplication or division with 0. So 3 root 2 has to be proven that it is an irrational number. The methodology is same, proof by contradiction method. So we start with the assumption that 3 root 2 is rational and ultimately proving that our assumption is wrong and concluding that 3 root 2 is irrational. So not only the numbers that are mentioned here, please try with few other combination of a rational number and irrational numbers, any operation between them, addition, subtraction and multiplication and division, except that the rational number should not be 0, because 0 makes any number, be it rational and or irrational, to be 0, and any number, rational or irrational, when divided by 0, we again get 0. And any number divided by 0 is undefined. So except those three cases which we saw earlier in the video, pick up any other numbers, a rational number and an irrational number, and any operation between them, plus, minus, multiplication or subtraction, and go through the method and practice it. Let's revisit the operations between rational and irrational numbers to stress the point that we should be little careful when 0 is involved, especially in multiplication or division. Earlier in the video, we saw that any operation, addition, subtraction, multiplication or division of a rational number and an irrational number is always irrational, except when that irrational number is in either multiplication or division with 0, as 0 is a rational number and the result would also be 0 or undefined. So any rational or irrational number
when multiplied with 0, the result is 0. And 0 is rational, as we know. So in this case, this rule does not apply, that the operation of a rational number or irrational number is irrational. So even if you multiply a rational number or irrational number with 0, the result is going to be 0. And 0 when divided by a rational number or an irrational number again will give us 0. And any rational or irrational number when divided by 0, the result is undefined. So except in these three cases, the operations, any operation between a rational number and irrational number is always going to be irrational. So the numbers that you have to pick to practice the proving irrationality questions, pick up any number other than 0, because when 0 is involved, the results are rational number and undefined when it comes to multiplication or divisions. So pick up any numbers other than 0 as a rational number and pick any irrational number and practice proving irrationality. After seeing good bit of what are irrational numbers and their proofs, now let's see what are rational numbers and their decimal expansions in bit more detail. A quick recap of what is a rational number. It is a number that can be expressed in p by q form, where q is not equal to 0. And it can also be defined as a number whose decimal expansion is either terminating, or if it is not terminating, it is recurring. In other words, few digits keep on repeating. We have seen few examples as well in the earlier part of the video about what is a decimal expansion, what is its meaning. So decimal expansion terminating means at some point of time in the division, the remainder becomes 0. In non-terminating cases, digits keep on repeating. It is the same remainder we keep getting again and again, and in the quotient, the digits keep on repeating. Now the question is there any way that we can find when p gets divided by q, our rational number, when does it terminate and when it is not terminating but the digits keep on repeating? What are those conditions? Let's see in bit more detail. All the way up to class 10, we solved many problems, and as part of solving those problems, we did a lot of calculations in terms of additions, subtractions, multiplications, and divisions. So what is that number that comes to our mind which is easy to work with when it comes to multiplication or division? Give it a thought. Turns out 10 and its powers are relatively easy to work with when it comes to multiplication or division. Of course, 10 and its powers are relatively easy to work with even in addition and subtraction as well. But here our focus is on multiplication and division. So let's see a few examples of multiplication of a number with 10 and its powers. So let's pick an example 12. 12 into 10 will give us 120. Here we don't need to do the traditional multiplication. We just have to keep the number as it is and add 1 0 to the end of the number, because 10 has got only 1 0. Another example, 392 into 10 will give us 3920. Here also we have to keep the number as it is and add 1 0, because we are multiplying with 10 and 10 has got only 1 0. Another number, when multiplied with 100, which is a power of 10. Here also we have to keep the number as it is and add 2 zeros to the end of the number, as 100 has 2 zeros. Not only the integer numbers like this, even for decimal numbers also, when multiplied with 10 or its powers, it is easy to work with. So in this example, 14.56 multiplied by 10 will give us 145.6. All that we need to do is that move one decimal digit, the first decimal digit, to the left of decimal point. And when a decimal number is multiplied with 100, we have to move two decimal digits to the left of decimal point. So 18.562 multiplied by 100 will give us 1856.2, and so on. So when multiplied with 1000, we'll move 3 decimal digit to the left of decimal points, and so on. Now let's see some examples of division with 10 and its powers. Again, picking up 12, 12 divided by 10 will give us 1.2. Here also we don't need to do the traditional division. We just have to move one digit to the right of decimal point. As 10 has got only 1 0, so one digit will move to the right of decimal point. And not only for composite numbers like 12, same is the case with prime numbers like 17. So 17 divided by 10 will give us 1.7. We just have to move one digit to the right of decimal point. And when some number is divided with 100, and because 100 has two zeros, two digits will move to the right of decimal point. So 23 divided by 100 will give us 0.23, and 392 divided by 100 will give us 3.92. 9 and 2 are moved to the right of decimal point here. And when some number is in division with 1000, because 1000 has 3 zeros, 3 digits will move to the right of decimal point. And even for decimal numbers also, same is the case. Here 100 has two zeros, so two digits will move to the right of decimal point. So let's try to quickly summarize what we have discussed so far. If an integer is getting multiplied by 10, we put the number as it is and add 0 to the end of the number, because 10 has only 1 0. So we just add 1 0 to the end of the number. Similarly, if a number is getting multiplied with 100, which is a power of 10, we keep the number as it is and put two zeros to the end of the number, as 100 has two zeros. And if a number is getting multiplied with 1000, then we put the number as it is and add 3 zeros, as 1000 has 3 zeros, and so on. And when a rational number like 14.56 expressed in decimal form, when it is getting multiplied with 10, we just have to move one digit, the first decimal digit, to the left of decimal point. And similarly, any decimal number or rational number is getting multiplied with 100. We just have to move two digits to the left of decimal point. As here in this case, 10 has got only 1 0, so one digit gets moved to the left of decimal point. And 100 has two zeros, so two digits will move to the left of decimal point. And similarly, when any rational number or decimal number gets multiplied by 1000, three digits will move to the left of decimal point, and so on. So please try taking different integers and different rational numbers or decimal numbers and try actual or traditional multiplication and see whether you are getting the same results in line with what we have discussed so far. Now let's turn our attention to division. And this is the main topic here, as our interest is to check on decimal expansions, whether they are terminating ones or non-terminating repeating ones. So our focus is on division. So in short, when a number gets divided by 10, only one digit will move to the right of decimal point, as 10 has only one zero. When any number gets divided by 100, two digits will move to the right of decimal point, as 100 has two zeros. And similarly, some number getting divided by 1000, three digits will move to the right of decimal point, as 1000 has three zeros in it. So please try with various examples and then see if the results are in line with what we have discussed. One important thing to note here is that 10 or its powers are easy to work with in multiplication and division anyway, especially when it comes to division. One more point what we will observe is that apart from being easy to work with, easy to divide, 10 and its powers terminate the decimal expansion. Please try with various numbers and check the results whether the decimal expansion of the P by Q form is getting terminated or not. Indeed, you will find that it is getting terminated. So 10 and its powers are easy to work with when it comes to multiplication and division. Most importantly, the division of any integer or rational number when divided by 10 or its powers can surely terminate the decimal expansion. So if 10 and its powers can terminate the decimal expansions, then the question would be, are there any other numbers that can also do the same? That is, what other numbers can terminate the decimal expansion of integers and rational numbers? Recall one of the general divisibility rules that we saw earlier in the video. If a number x is divisible by another number y, then x is divisible by each of the factors of y as well. Here our y is 10 and its powers. So if 10 can terminate the decimal expansion of any integer or rational numbers, the factors of 10, which are 2 and 5, should also be able to terminate the decimal expansion of any integer or rational number. Also, the powers of 10 will have only 2 and 5 as the prime factors. So as powers of 10 can terminate the decimal expansions, powers of 2, powers of 5 can either individually or together should be able to terminate the decimal expansion of any integer or rational number. So if 10 or its powers are in the denominator, then we can straight away say that the decimal expansion is terminating. But many a times the denominator may not be directly in the tens or its powers directly. It could be in some combination of powers of 2 and powers of 5.
So let's see some of these forms now. So 2 alone can divide and make the decimal expansion terminate. So 2 is in the form of 2 power 1 and 5 power 0. As 5 power 0 is 1 and 2 power 1 is 2, so 2 into 1, 2. Same is the case with 5. 5 alone can terminate the decimal expansion of any number. So it can be written as 2 power 0 and 5 power 1. 2 power 0 is 1 and 5 power 1 is 5. So 1 into 5, 5. Note that not only 2 powers of 2, also not only 5 powers of 5 can also terminate the decimal expansion of any number. And we know 10 can terminate this decimal expansion of any number, so it can be written as 2 power 1 into 5 power 1. Similarly, 100 is 10 into 10, which is a power of 10, 10 square, can be written as 2 into 5 into 2 into 5, so 2 power 2 into 5 power 2. Similarly, 1000, 10 into 10 into 10, a power of 10, 10 power 3, can be written as 2 into 5 into 2 into 5 into 2 into 5, so 2 power 3 and 5 power 3. 2 power 3 into 5 power 3. So in general, if the denominator is of the form 2 power m into 5 power n, then we can conclude that the decimal expansion is terminating. So let's see a few important points of this form. M and n can be equal, or they need not be equal as well. It should be in the some powers of 2 and some powers of 5 form. And the important point is that m and n should be greater than or equal to 0. So if this condition is getting met, then the decimal expansion of any number is going to terminate. One final point, the denominator should be only and only in this form. If any other number apart from this form or any other number, then the decimal expansion is going to be a non-terminating repeating one. Let's see a few examples. So let's start with our first example, 17 by 8. So here 8 is in the denominator. So if we expand 8 into its prime factors, it would be 2 into 2 into 2, 8. So it is in the powers of 2 form. So we can straight away say that 17 by 8 is terminating. But still, just to show in the standard 2 power m into 5 power n form, we can write it as 17 by 2 power 3, or in other words 17 by 2 power 3 into 5 power 0. And we know that 5 power 0 is 1, so 2 power 3 into 1 is 2 power 3. And if we actually do the division, what we find is that we get 2.125, and at this stage the division ends. That means the remainder is 0 and the division stops and the decimal expansion has terminated. So 17 by 8 is a terminating decimal expansion. Another example, 35 by 50. So here we have 50 as the denominator, so expanding it 5 into 10, and further expanding it 35 by 5 into 2 into 5. So writing in the standard form 5 power 2 into 2 power 1. So this is in the standard form that we want to see. So 35 by 50 is a terminating decimal expansion. Of course, the moment we see 5 and 10 itself, we can conclude because 5 alone can divide, and 10 we know anyway can divide and make the decimal expansion terminate. This is just to show in the standard form. And if we actually divide 35 by 50, then we get 0.7 and the division ends there as the remainder becomes 0 and the division stops. So 35 by 50 is a terminating decimal expansion. Another example, bit longer one. Here we can, if we can spot that 16 is 2 power 4, here itself we can conclude that it's a terminating decimal expansion, because powers of 2 alone can divide and make the decimal expansion terminate, and 100, which is a power of 10, anyway we know that the decimal expansion is going to terminate when 100 is in the denominator. So just to show in the standard form, it would be 15 by 2 power 6 into 5 power 2 form. So 15 by 1600, the decimal expansion is going to terminate. And if we do the actual division, we get this number. And after that, the division ends and the decimal expansion terminates. Now let us see a few more examples of terminating decimal expansions, but more trickier ones. Our first example is 15 by 6, and here 6 is in the denominator, and expanding 6 we get 2 into 3, as 2 and 3 are the only factors of 6. Of course, 1 is a factor of any number, so let's keep 1 aside. So 6 is 2 into 3. So 2 is there, and we know that 2 can terminate the decimal expansion, but along with 2, 3 is also there, which is not part of the 2 power m into 5 power n form. So we may jump to conclusion that 15 by 6 may have a non-terminating repeating decimal expansion. In this case, just take a look at the numerator as well, and then see if these numbers which are not necessary for us can be cut off. So expanding 15, we get 3 into 5. So here 3 can be cut with 3. So what remains is 5 by 2, and we know that if 2 alone is in the denominator, then the decimal expansion terminates. So what remains is 5 by 2 here after cutting 3 with 3, and 5 by 2 is nothing but 2.5 if we do the actual division. So it's a terminating decimal expansion because the remainder becomes 0 and the division ends there. Another example, 35 by 28, and here 28 is in the denominator. So expanding 28, we get 4 into 7. So 4 is a power of 2 square. So it can terminate the decimal expansion, but 7 is also there, which is not part of 2 power m into 5 power n form. So in this case, also just take a look at the numerator and then see if we can get rid of this 7. So expanding 35, we get 7 and 5. 35 is equal to 7 into 5. So here we can cut 7 with 7. And what remains is 5 by 4. And 4 is a power of 2. So the decimal expansion terminates. Because powers of 2 alone can terminate decimal expansion of any integer or rational number, as we discussed a few moments ago. And if you do the actual division of 35 with 28, we get 1.25 and the division ends there, as the remainder becomes 0 and the division stops. So 35 by 28 has a terminating decimal expansion. Similarly, 77 by 22,
expanding the denominator 22, we get 11 into 2. So 11 is not part of our standard form, 2 power m into 5 power n. So just take a look at numerator as well. And 77 can be written as 11 into 7. So here 11 is getting cut off with 11, and what remains is 7 by 2. And 2 we know can terminate the decimal expansion. And if we actually do the division of 77 with 22, or rather 7 with 2, we get 3.5, and the decimal expansion terminates as the remainder becomes 0 and the division stops. Now let's take a look at some of the non-terminating, recurring or repeating decimal expansions. Our first example is 23 by 6. So expanding 6, we get 2 into 3, and 3 is not part of our standard 2 power m into 5 power n form. So taking a look at 23, 23 can be written as 1 into 23 only, as 23 happens to be a prime number, and it has only 1 and itself as the factors. So expanding 23, we get 1 into 23 only, and there is no way that we can get rid of these 3 here. So we can't cut, as the numerator doesn't have a factor 3 for 23. So the denominator is not in the standard 2 power m into 5 power n form, because 3 is there. So we can conclude that 23 by 6 is a non-terminating decimal expansion. And if we do the actual division, we get 3.8, 3333. So the digit 3 keeps on repeating. Another example, 34 by 9. Expanding 9, we get 3 into 3. So surely this is not in the 2 power m into 5 power n form. So let's see if we can get rid of the 3 here from the denominator. So 34 can be written as 17 into 2, and we cannot go any further because both 17 and 2 are prime numbers. So there is no way we can get rid of both these 3's. If we can get rid of both these 3's, then the denominator will be having 1, and 1 is in the form of 2 power 0 into 5 power 0 form. So 2 power 0 is 1 and 5 power 0 is 1. So 1 into 1, 1. And 1 we know can cut any number. But here there is no way that we can get rid of the 3's here. And the denominator definitely not in the 2 power m into 5 power n form. So the conclusion is 34 by 9 is a non-terminating decimal expansion. And if we do the actual division, we get 3.77, where the digit 7 keeps on repeating. Another example, 15 by 35. So expanding the denominator, 35 can be written as 5 into 7. And 5 is there, but 7 is not part of our standard 2 power m into 5 power n form. So let's see if we can get rid of this 7. So 15 can be written as 3 into 5. So only 5 can be cut with 5, and what remains is 3 by 7. And definitely it is not in the standard 2 power m into 5 power n form. So we can conclude that 15 by 35 is a non-terminating decimal expansion. And when we do the actual division, we get these decimal numbers, and 285714 keeps on repeating, as you can see. 285714, 285714. So 285714 keeps on repeating again and again as we continue the division. So 15 by 35 is a non-terminating decimal expansion. So here are three theorems based on what we discussed about rational numbers and their decimal expansions. So first theorem, let x be a rational number whose decimal expansion is terminating. Then x can be expressed in the form of p by q. So because x is a rational number, it can be expressed in p by q form, where p and q are co-primes. Then the prime factorization of the denominator q would be in the 2 power m into 5 power n form, where m and n are non-negative integers, greater than or equal to 0, in other words. So simply put, if x is a rational number and its decimal expansion is terminating, then the denominator q would be in the form of 2 power m into 5 power n form. The second theorem is a converse of the first one. So what it says is that if x is a rational number in the p by q form, and if q is in the form of 2 power m into 5 power n form, then x, the decimal expansion of x, terminates. So it's a converse of the first theorem. And the last theorem is kind of negation of the first two theorems. So if x is in the p by q form, where and it's a rational number where p and q are co-primes, and if the form of q, which is our denominator, if it is not in the form of 2 power m into 5 power n form, then x's decimal expansion is a non-terminating, repeating or recurring one. And that completes the theory and concepts part of real numbers. Hope this video is helpful in clearing up the concepts for you, and hope your time is well spent and productive. If you find this video helpful, drop a comment with any questions, suggestions, or just let me know which part clicked for you. Thanks for watching, and I'll see you in the next video.